Greetings, organickers. Welcome to your very first organic chemistry video. I'm sure you've heard lots of things about organic chemistry, some good and some bad, and hopefully through this course I can convince you that perhaps those bad things you heard about organic chemistry were a little bit exaggerated. So let's go ahead and get started. We're going to begin with something that should be review for most of you, and this is on writing Lewis dot structures. The Lewis dot structure is a way of putting atoms and electrons together to make molecules. We draw them only for covalent molecules, because remember that there are two types of bonding, ionic and covalent. And ionic is simply the transfer of one or more electrons from one atom to another atom. A covalent bond, on the other hand, is the sharing of a pair of electrons between two atoms. Let's look at the steps. The first thing that you're going to do is figure out the total number of valence electrons supplied by all of the atoms in the structure. We only take into consideration the valence electrons, not all of the electrons in the atoms. So how do I find out the number of valence electrons? Well, I go to my periodic table and I look for the group number. Make sure that you're using a periodic table that uses the American convention, and in the American convention we skip over these transition metals when we're numbering from one group to the next. So I'll find my atom. For instance, if my atom of interest is boron, boron is right here. I see that boron is in group number 3, and that means that it has 3 electrons in its valence shell. I'm going to do this for every atom in my molecule, and then I'm going to sum them up. Next, I'm going to add electrons. For every negative charge, I'll add 1 electron. For any positive charge, I'm going to subtract 1 electron. In the next step, I am going to arrange the atoms, connecting them with single covalent bonds. Now let me just pause for a moment here and say that this is often the most difficult and confusing part for students. Probably your best approach is to determine which atom has the highest valence. And by highest valence, what I mean is the atom that can make the most bonds. Then you're going to make that atom the central atom and arrange the other atoms around it. This will work for you much of the time. It's not going to work for you every time, though, but it's a good place to start. And keep in mind that writing Lewis dot structures is often a process of trial and error. You may put together a structure and then find that you cannot arrange all of the electrons around the atoms and obey the octet rule for every atom. So you may have to start over again with a different skeletal arrangement of atoms. You should consider the normal bonding patterns for each element in your molecule. And what do I mean by that? Well, as we progress and start drawing more and more Lewis structures, you'll probably notice these bonding patterns begin to emerge. For instance, hydrogen and the halogens, that would be fluorine, chlorine, bromine, and iodine, all form only one covalent bond. That is their normal bonding mode. Oxygen typically forms 2 covalent bonds, nitrogen 3 covalent bonds, and carbon 4 covalent bonds. I'm going to explain this to you a little bit further in a later video. All of the elements that I've listed here are either first or second row elements. First row elements, hydrogen, can only have 2 electrons in its valence shell. Second row elements must obey the octet rule. They can only have a maximum of 8 electrons in their valence shell. However, third row elements, such as sulfur, which is right under oxygen, phosphorus, which is right under nitrogen in the periodic table, can expand their valence shell. When you're drawing a Lewis dot structure, if you find that you have extra electrons that you're not quite sure what to do with, if you have third row elements in your molecule, you should probably give those electrons to the third row elements. Third row elements will exhibit bonding patterns that are similar to the element that's directly above them, but they can have additional bonding patterns as well by virtue of their ability to accept additional electrons. So here we see normal covalent bonding patterns, and as I've mentioned, we're going to look at this in a little more detail in a later video, but just briefly I'll tell you that carbon wants to form 4 bonds. Those 4 bonds can be composed of 4 single bonds, 2 single bonds and a double bond, 2 double bonds, or a single and a triple bond. So there's different ways that carbon can make those 4 bonds. You'll notice that nitrogen wants to form 3, and typically nitrogen will have a non-bonding pair. In other words, we call that a lone pair of electrons. Oxygen typically forms 2, and halogens 1 covalent bond. So now you've figured out how many electrons this molecule will have. You've made a skeletal arrangement connecting the atoms with single bonds. So you're going to distribute the pairs of electrons around the atoms so that each atom, with the exception of hydrogen, has 8 electrons in its valence shell. Or in other words, you're going to satisfy the octet rule. Hydrogen, as a first row element, can only have 2 electrons in its valence shell. If you find that you don't have enough electrons to give each atom 8 electrons with your single bonds, the atoms that are sharing electrons may have to share more than 1 pair of electrons. You may have to move electrons to form double or triple bonds between 2 atoms, and you're going to be moving those non-bonding pairs of electrons as needed. Compute the formal charge and evaluate the structure. Very often, computing the formal charge on each atom in a Lewis dot structure that you have drawn can indicate whether your Lewis dot structure is correct or not. If the species that you're drawing the Lewis dot structure for is charged, then 1 atom will have to have a charge in your Lewis dot structure. If it's neutral, atoms will either have no charges, or the charges will have to neutralize one another. So it's a good way to check your Lewis dot structure. We're going to talk about formal charge in a later video, so I'm not going to spend any more time on that just now. Let's look at some simple examples of diatomic molecules. And let's look at fluorine. First thing you want to do is figure out the number of valence electrons that you're going to have to account for. So we go to our periodic table and we look for fluorine. And we can see that fluorine is in group 7. That means that each fluorine has 7 electrons in its valence shell. So each fluorine will contribute 7 electrons. So I have 2 fluorines. 2 times 7 is 14 for a total of 14 electrons. I'm going to connect the 2 fluorines with a single bond. So a single bond is composed of a pair of shared electrons between 2 atoms. So I can represent this pair of electrons as 2 dots, a dot for each electron, but very often we represent that pair of electrons that forms a bond as a line. And I'm going to be doing this in the future. So that line represents my first pair of electrons that I've used. I have to distribute the remaining 12 electrons to satisfy the octet rule for the 2 fluorines. So let's go ahead and do that. I have 2 for the bond. Now I have 4, 6, 8, 10, 12, 14. So I've distributed all of my electrons, and let's just check and see if we've satisfied the octet rule. This fluorine has 8 electrons in its valence shell. It has 3 non-bonding or lone pairs of electrons for 6, plus it's sharing 2 with the adjacent fluorine. The same is true for the other fluorine. So this is my Lewis dot structure for F2. Let's look at oxygen. Again, we go to our periodic table, we look for oxygen, and we see it is in group 6. So each oxygen will contribute 6 electrons to our Lewis dot structure. So I have 2 times 6 for 12. Connect the 2 oxygens with a single bond. I've used 2 electrons. I have to distribute the remaining 10. So I have 2, 4, 6, 8, 10, 12. Now if I look at this structure and evaluate it, I can see that this oxygen has 8 electrons in its valence shell, but the oxygen on the right only has 6. It's got 2 lone pairs, and it's sharing a pair. These 2 oxygens are going to have to share more than 2 electrons. So I'm going to take one of the non-bonding pairs of electrons and push it towards the adjacent oxygen to form a new bond. Now I have a double bond between the two oxygens, and if you evaluate this Lewis dot structure, you will see that each oxygen has 8 electrons in its valence shell. Let's have a look at nitrogen. Calculate the number of valence electrons. If you go to your periodic table, you'll see that nitrogen is in group 5, 5 electrons from each nitrogen for a total of 10. Connect the two nitrogens with a single bond. Now I add the remaining electrons to satisfy the octet rule. I've used 2, I have to add 8 more. So I go 2, 4, 6, 8, 10. Again, if I look at this structure, I can see that each nitrogen has only 6 electrons in its valence shell. So I'm going to have to start to make some additional bonds using the non-bonding pairs of electrons. These nitrogens have to share more than one pair of electrons. If I push a pair of electrons from this nitrogen and form a new bond, I've satisfied the octet for the nitrogen on the right, but I still haven't satisfied the octet for the nitrogen on the left. So I have to push a pair of electrons from the other nitrogen to form a third bond between the two nitrogen atoms. Now I have a triple bond between the two nitrogens, which accounts for 6 electrons. My 2 lone pairs, or non-bonding pairs of electrons, give me another 4 for my total of 10. Each nitrogen has 8 electrons in its valence shell. Well, we've looked at some very simple diatomic molecules. In our next video, I want to take a look at some triatomic and larger molecules.